want to talk a little bit about work and energy. I'm actually going to talk more about work right now than about energy, but the two are intertwined, and so you really can't talk about one without talking about the other one. And so I'm going to introduce the topics together and then focus on work. A little bit on the terminology first. Energy is a condition, it's a state, it's a property. It's just something that an object needs in order to do work. Now, then work is basically the process of one object when it transfers some or all of its energy to another object. So work is the process of transferring energy. Energy is what you need to do work with. And that's why they're kind of related. One depends upon the other. From the sense of parts of speech, I guess, you would say energy is a noun and work is a verb. And that's kind of the relationship between energy and work. I tend to think of it as energy is the money you have. Work is the process of spending that money to buy something. So that's a brief introduction on energy and work. Let's just focus on work a little bit. I'm not going to really draw it out a whole lot, but I'm just going to simply say in the physics world, because we all have our own definitions of work, work is done when a force is applied to an object and the object moves. That's an important part. Both parts have to be true. You have to apply a force to the object, and the object has to move because of that force. That's when you have work. And here's our basic equation for work. It's force times displacement. If you look at the units, force is newtons, displacement is meters. That gives us Newton meters. This is called joules, which what you're going to find out, if you don't already know, are also the units for energy. But work and energy are related, are basically the same thing, and so they should have the same units. Work is what is done to transfer energy to an object. By applying the force and making the object move. If the object does not move, energy was not transferred. No work was done. This is like pushing on a wall. I don't care how hard you push on that wall. If the wall does not move, you did not do work on the wall. And so you did not transfer energy to the wall. Now, you might actually start breathing harder and your face might get red if you're pushing hard enough, but that's because your body is doing work. Your heart's beating faster to pump more blood, to try and flex the muscles. So there is work being done inside your body, but no work is being done on the wall. No energy is transferred to the wall. And that's the important thing about work. With work, we're doing work on an object. We're making an object move. We're transferring energy to that object. And it's to a specific object. Let me take a look at how the direction of the force impacts the displacement of an object. Let me do a simplified example to illustrate this. Let's just say we have a box on the ground. That's not a very good box, but you get the idea. The direction of the force, we might be pushing down on it at some angle like this, and let's say this angle is theta. And then the box is moving in this direction. That's the displacement. And here's the thing to understand, that this force can be broken up into so much is in the y direction and so much is in the x direction. This component in the y direction, since there's no displacement in the y, there is no work being done in the y direction. No work in y. So this component is doing no work on the box. But the x component of the force is causing the displacement. And that's what's doing the work. And if we break up that, that's force times the cosine of the angle. So in our work expression, what we would have, when we had work is Fd before, what we now have is work is the force times the cosine of the angle between force and displacement. And if I look at it in another sense, this angle right here would be the same if I drew the force down there and this was the angle. These two angles are the same. And so that's the x component of the force. If I was pushing it straight down, the box would not move. And so this force is doing no work, primarily because theta is equal to 90 degrees, which means the cosine of my angle, the cosine of 90, is 0. But that makes sense. If I'm pushing straight down on the box is not going to move to the side. I'm not going to do work. It's only the component of the force that's in the same direction of the displacement that is actually causing the work. That's why we write the equation like this. This is my overall net force. This is my displacement. This represents the component of the force, component of F, actually doing the work. So here's our equation for work. Work is force times the cosine of the angle between the direction of the force and the direction of the displacement. In the higher physics sense, this is the dot product. You're taking two vectors, multiplying each other, and we're getting a scalar, because work is a scalar number. More importantly, the concept behind this is that only the component of the force that actually causes the object to displace does the work. The other component does not work. In the example that I just looked at, the downward component does not cause the object to be displaced vertically. So the downward component of the force does no work on the object. It's only the horizontal component, the component in the same direction as the displacement, does the work. That's a critical thing to keep in mind. Now, I said force is a vector, displacement is a vector, but work is a scalar. Sometimes when you multiply two vectors together, you get a scalar, as in this case. Work has no direction, but you can do positive work and you can do negative work, because that's saying work is going into the object or work is coming out. But this negative energy, this negative work that we do, isn't based on the direction, it's based on the energy flow. Let's look at an example here and look at what the work is in each of these situations. So, when we're lifting a box, the force is directed upwards. The displacement of the box is upwards. If force and displacement are in the same direction, the angle between force and displacement is 0 degrees, and the cosine of 0 is 1. So work is simply force times displacement. Pretty straightforward. When we're carrying a box, and I'm not going to get into all the little technicalities on friction, but when we're carrying a box, our force is still upward because we're holding it up. But the displacement is side to side, horizontal, which means the angle between force and displacement is 90 degrees. The cosine of 90 is 0. So we're doing no work on the box carrying it. In other words, we're not transferring energy to the box. Again, not to say our bodies aren't doing work, we're just not transferring energy to that box. Now, Here's where it gets a little complicated. When we're lowering a box, the force is still upwards. It's just we're easing it down. The displacement is down. And so the angle between the force and displacement is 180 degrees. And the cosine of 180 is -1. And so here's an example of where we're doing negative work on the box. Energy is coming out of the box. And when we talk about energy in a little while, we're going to talk about what type of energy we're talking about. But when we're lifting a box, we're putting energy into the system. Energy in. And here, energy is coming out of the box. I don't know. So here's a practice problem. A 20-kilogram suitcase is raised up 3 meters above some platform. We want to figure out how much work is done on the suitcase. Force is up. Displacement is up. Theta between the two is 0. The cosine of 0 is 1. So what we're looking at is just force. Work is force times displacement. The force that we have to overcome when we're lifting something is the force due to gravity, which is just mg. So our work equation becomes force times displacement, or the force of gravity times displacement, mg times displacement. So I have 20 times 9.8 times 3. We're doing 588 joules of work just to lift it up. Here's where work and energy are related. Work changes the energy level of an object, and this is the big idea. Since work transfers energy either into or out of an object, the energy level of the object is going to change because of work. If we do work on an object, we're transferring energy to that object, and then that object can use that energy to do work, which transfers its energy to something else. And that's the process. You do work on something to give it energy. That something can do work on something else and transfers that energy along. If no energy change occurs, this is the hugest idea. If no energy change occurs in the object, no net work was done. If net work is done, you have to have an energy change, and this is our link between energy and work. And this is a real key idea.